In this lesson, you will learn how to identify nonlinear functions. Now, you might recall that linear functions have a constant rate of change. Because of this attribute, the graphs of linear functions are straight lines. Now, a nonlinear function does not have a constant rate of change. And because of this, nonlinear functions have all sorts of different shapes when they're graphed. Now I want to talk about a few different examples of nonlinear functions. And let's take a look at a graph together and we'll talk about the first set. Here you have two graphs that represent exponential functions. Now when an exponential function is increasing, it is called exponential growth. And when it is decreasing, it is called exponential decay. Now the general form of an exponential function is f of x equals b to the power of x. Now remember, f of x is just another way of writing y when you're writing an equation as a function. Now the graph on the left is increasing because it's curving upwards, right? You can see the graph moving upwards. This is an example of exponential growth. Now the graph here on the right is curving downwards as the x values increase. That means it's decreasing, or you could say this is a graph of exponential decay. Now, exponential functions aren't the only type of nonlinear function that we're going to talk about. Let's move on to quadratic functions. Now, I'm going to show you a graph for quadratic, and then we're going to talk about the different features of quadratic functions and maybe some examples that will help you understand them better. A quadratic function is an equation with a variable that is squared. For example, you can have f of x equals x squared, or something like f of x equals 3x squared plus 2. Both of these are examples of quadratic functions. Now, a real-life example of a quadratic function would be something like shooting a basketball. The path of the basketball follows an arc, right? It goes up for a little bit, and then it hits a peak, and then it comes back down. Now, this type of path can be modeled by a quadratic function. So maybe they're a little bit more real-life than you expected. Now, if you take a look at the graph here, a quadratic has a U-shape appearance when it's graphed. And what this is called is a parabola. Now, parabolas can open up, right, where this one is an example of pointing upwards, and the parabola can be in any of these quadrants. Another example of a parabola could be opening downwards, like this. That's a crude example, but in general, you've got upward facing or downward facing, and the other mark of a quadratic is having a variable that is raised to the power of 2. Now let's talk about a third example of nonlinear functions, and this will be the piecewise function. Maybe not surprisingly, a piecewise function is defined in pieces, and it might have several different equations for different values of x. For example, I have a graph here that represents two functions. The first function is f of x equals 3, and this occurs when, right, this is a hallmark of a piecewise function, right? You're given different domain values for different functions. So f of x equals 3 when x is less than 2. So notice there's no point here at x equals 2 for the red line, but x equals 3 for all points when x is less than 2. Next, we've got this blue line here, which is represented by the function f of x equals x squared minus 4. Now, do you remember when you have a squared what that is? That's a quadratic, so you expect to see a parabola. Now, I know this looks like a straight line, but actually it is curved. So this is part of a parabola from a quadratic function. And if you continued this, right, if you didn't have domain restrictions, you would see a larger u that would come around something like that, follow that path. But there are restrictions. F of x equals x squared minus 4 when x is greater than or equal to 2. So that's why you see a dot here for the value 2, because it's including equals to. And you have all the values for when x is greater than 2 being mapped by this blue line. Now notice how the graph of either function, they don't overlap each other. Now if they overlapped at all, right, let's just say that this blue line extended down into here. Now this would no longer be a function because a function has to pass the vertical line test, which means you have to be able to draw a line vertically through the curve, and the line must only hit the curve once, but you would hit the curve twice. So this is important, right? So with a piecewise function, you won't have overlap between the different pieces that define the function. Otherwise, it's no longer a function. Let's talk about another example of a nonlinear function. Here we have a graph of an absolute value function. An absolute value function is actually an example of a piecewise function. So with an absolute value function, you're looking for those absolute value symbols. And recall that when you take the absolute value of any number, the answer is positive or 0. Examples of absolute value functions include stuff like f of x equals the absolute value of x, or something like f of x equals 2 times the absolute value of x plus 1. Now the graph of an absolute value function is really distinct. It's V-shaped. As you can see, it goes in straight lines in both directions in the shape of a V. Now the reason this happens is because the value of y will always be the same for both x and negative x. So we can highlight this concept. Look at this graph, right? When x equals 1, y equals 1. We've got the point 1, 1. Let's look at the opposite of this x value. So we did x equals 1. The opposite of that would be x equals negative 1. So let's take a look. When x equals negative 1, y equals 1. So negative 1, 1. And this will actually occur for all points on the graph. And that happens because of this absolute value function here. So it doesn't matter if x is negative or positive, because after the absolute value is taken, everything ends up being positive. So the domain for an absolute value function would be all possible x values, or all inputs. So the domain is essentially all real numbers, right? And then for this graph in particular that we're looking at, it opens upwards and all the y values are positive. So that means the range, right, which covers y values, is from 0 to positive infinity. And 0 is the bottom because, again, all the y values are positive in this case. And positive infinity is the maximum because these values can continue on forever and ever and ever because the domain is all real numbers. Now let's take a look at the last example of a nonlinear function, which is called the stepwise function. A step function graph has line segments that resemble steps with gaps in between each one. So you can see you've got this blue line, and then there's this gap here, and then the red line continues on. Now the graph here is modeled by the equation, or is modeling the equations y equals 3 when, and again, this is another example of a piecewise function because you have definitions about the domain. So y equals 3 when x is less than or equal to 5. And then the next function we have here is y equals 6 when x is greater than 5. So a real world example would be something like, how about a scenario with package size and the shipping cost? So maybe for something like a small package, right, this would cost $4. The next step up, right, would be a medium package, and that might cost something like $6. And then lastly, if you have a large package, you would have $8. Now the example I've given you here, as well as the graph, are functions that are increasing because the steps are moving up the y-axis. In this lesson, you've learned how to identify different types of nonlinear functions. Thanks for watching.